This third technique for solving systems is called the addition method. Sometimes in some textbooks it is called the addition/elimination method. Addition is what you do, elimination is what happens. The addition method is based on this premise. If you have a statement of equality, 5 is equal to 5, and you add it to another statement, which is equal, 3 is equal to 3. Let's suppose we add those. When you add them, you get another statement which is also a statement of equality. So if you add things that are equal to each other, you will get a new statement of equality. That seems like a silly idea, or maybe just so simple, but it is the reason that the addition technique works. When we add linear equations together, we get a third linear equation. The linear equation we get shares the point of intersection with the first two. So it contains the same point. All right, we will not be looking at the graphs, but I wanted to mention it in terms of graphing. Let's take a look at these. Now the first system that we have is negative 5x plus y is equal to 12, and 3x minus y is equal to negative 10. If we want to use the addition method, we want x's to line up, y's to line up, equal signs to line up, and constants to line up. We need them to line up so that like terms will be added. The other thing that we need is we need either in the x's or in the y's, we need a pair of opposite coefficients to exist. And we have them here. We have positive 1 and we have negative 1. So just like with substitution, we needed a certain thing for it to be ready. In substitution, we needed either an x equals or a y equals. With the addition method, we need either the x's or the y's, one or the other, so that they have opposite coefficients. So we'll be looking for that to see if the system is ready. Well, this one is ready, so we will add. And when we do, we have negative 5x plus 3x is negative 2x. The y's cancel out, equal sign, positive 12 and negative 10 is 2. We eliminated the y's from the problem. Divide by negative 2, and we get x is negative 1. Okay, so when a system is ready for elimination or for addition, it is very quick to get the first variable. Now, find y. When we do this method, we don't have a circled equation to go grab. So you grab either equation. It just doesn't matter which one. Sometimes one is a little easier than others. Sometimes people say, if it doesn't matter, then I'm just going to grab the first one. It doesn't matter in this case. So I'm going to take negative 5x plus y is 12. Take either equation. They'll both work. Plug in the value you got for x. So it's negative 5 times negative 1 plus y is equal to 12. Positive 5 plus y is equal to 12. Subtract that 5, and y is equal to 7. We got an ordered pair solution, negative 1, 7. So I will choose A, negative 1, 7. No matter what order you get the answers in, whether you get y first or x first, the ordered pair has to have x, y order. All right, that's the addition method. Let's look at problem number 2. I have x minus 6y is equal to 35, and negative x plus 2y is equal to negative 15. Is this system ready for the addition method? Well, look at your x's. Those have coefficients of positive and negative 1, which are opposites. So the answer is yes, it's ready. Go ahead and add. The x's cancel out. I have negative 6 and positive 2 for negative 4y is equal to, that's going to be 20. Divide by negative 4, and y is negative 5. Now, find x. You get to pick. It doesn't matter. I'm just going to grab the first equation. X minus 6y is 35. Take this value for y and plug it in. X minus 6 times negative 5 is 35. That's x. Negative times negative is positive 30 is equal to 35. Subtract 30. And x is equal to 5. Once again, I got an ordered pair solution, and the ordered pair is positive 5 for x, negative 5 for y. That's my ordered pair. All right, let's look at a few more problems. Number 3. I have, let me get myself more room here. I have negative 5x plus y is equal to negative 7, and 2x minus 4y is equal to negative 8. Now, unfortunately, in this problem, the x's are not opposites, nor are the y's. So I have to do a little prep work to get it ready. The prep work that I use involves multiplying an equation by a certain number to create those opposites in the coefficients that I want. If I were trying to get the x's to have opposite coefficients, they would need to both be changed. They would need to both be changed to the least common multiple. The least common multiple of negative 5 and 2 is 10. That would be a little bit of work. We'll encounter one of those that we have to do later. Here, because this coefficient is an implied 1, it would be pretty easy to turn it into the opposite of this. All I'd need to do is multiply it by 4. So what I'm going to do is multiply the top equation by 4. That gives me negative 5, 4 times negative 5x is negative 20x. 4 times 1y is 4y. 4 times negative 7 is negative 28. Multiply every term in the equation, both sides, by that number. Keep the second equation, 2x minus 4y is equal to negative 8. It is now ready, so now I will add. That gives me negative 18x. The y's have canceled out, is equal to negative 36. Divide by negative 18, and x is equal to 2. Now, it does not matter, we've said this before, when you're going to now find y, it doesn't matter which equation you use. It doesn't matter whether you pick one of the original equations or one in the new system. It just doesn't matter. So if I grab the first equation, negative 5x plus y is equal to negative 7, and I plug in, that's negative 5 times 2 plus y is equal to negative 7. Negative 10 plus y is negative 7. Add 10 to both sides, and y is equal to 3. All right, I've solved the system. I have an ordered pair solution. The ordered pair is 2, 3, and that's what I would type in to the blank. Let's look at this one. I have 2x plus 3y is equal to 0, and 4x plus 6y is equal to 1. Now, this is not ready to add because I do not have a pair of opposite coefficients here or here. So, what is the least common multiple of 2 and 4? The answer is 4. What is the least common multiple of 3 and 6? The answer is 6. Now it is totally up to you to turn this into a -4. I would simply multiply it by -2. That wouldn't be hard, and this is already a 4. Or to get this to become the opposite of this, a -6, I would multiply it by -2. So it seems like I have a choice, but either way, I think I'll target the x's, and in order to make this 2x turn into the opposite of this, I'm going to need to multiply by -2. So there's a good bit of decision making that has to go on there. You need to think about what the least common multiple is, what 2 and 4 could both go into, or what 3 and 6 could both go into, and then how could you make that happen? So -2 times 2x is -4x. That's good. That's what I wanted. -2 times 3y is -6y. -2 times 0 is still 0. Underneath it, I have 4x plus 6y is equal to 1. And I'm ready to add. Now, I was targeting the x's, but in this particular problem, not only did the x's cancel, but so did the y's, leaving me with 0 on the left-hand side. On the right-hand side, when I add, I get a 1. When the variables drop out, I hope by now you recognize that you are in some kind of special situation. This is a false statement, meaning that these two lines share a point whenever 0 is equal to 1. Well, 0 is never equal to 1, so these two lines never share a point. There's no solution. I know that you couldn't tell this, but it does turn out these two were parallel lines. All right, let's look at just a few more. I have -2x plus y is equal to 2, and I have 8x minus 4y is equal to -8. This system is not ready for addition, but I can pick what I'm going to multiply by to make it become ready. The x's, the least common multiple is 8. I would have to multiply the top equation by a 4 to turn those into 8s. That wouldn't be bad. Second one, because this is a 1, the least common multiple here is this number. It's 4. I'm not worried about the sign yet. To get this 1 to become the opposite of this, I would just multiply by 4. Although it seems like something's going on, I'm going to target the y's, which means I'm going to multiply the top equation by 4. That will make that become a 4y. That's a -4y. I would have opposites. So let's see what happens. 4 times -2x is -8x. 4 times 1y is 4y. And don't forget, 4 times 2 is 8. Some people make mistakes by forgetting to multiply this chosen number times the constant. 4 times 8, oh, I'm sorry, I'm not multiplying the second equation, I'm just copying it down. Now, I think you noticed that although I targeted getting opposites in the y's, once again, I got opposites in both. So adding those together gives me 0, because I am adding now. On the right-hand side, I get another 0. The difference between problem number 4 and problem number 5 is the fact that this resulted in a true statement. And when it results in a true statement, that means that you have infinitely many solutions. These two lines intersect whenever 0 is equal to 0, and 0 is always equal to 0. So they always intersect. They are the same line. All right, we have one more. And it is 3x minus 3y is equal to 7, and 4x plus 6y is equal to 6. Well, what is the least common multiple of 3 and 4? What would 3 and 4 both go into? The answer is 12. You could multiply this by a 4 and this by a 3, one of them negative, to get a positive and negative 12. Okay? Over here, the least common multiple is 6. If you said it was 18, 18 is a common multiple, but it's not the smallest one. It would be pretty easy to make this coefficient become a negative 6. So it will be easier to turn both of these into 6s. I can turn this into a 6 by multiplying that equation by a 2. That gives me 2 times 3x is 6x, 2 times negative 3y is negative 6y, and 2 times 7 is 14. I don't need to change the second equation, so it stays 4x plus 6y is equal to 6. Add. That gives me 10x, those are gone, is equal to 20. Divide by 10. X is equal to 2. Now find y. I'll just grab the first equation. 3x minus 3y is 7. That's 3 times 2 minus 3y is equal to 7. 6 minus 3y is equal to 7. Subtract 6 from both sides. Negative 3y is equal to 1. Divide by negative 3. And y is equal to negative 1/3, because 3 doesn't go in there into 1. I know that seems unusual, but it is correct. We have the solution is 2 negative 1/3. Okay? I did want to show you one more thing that's not involved in one of these examples, but this could show up sometime and you need to be exposed to this. Suppose I had 2x plus 3y is 5, and 5x plus 4y is 8. Looking at this system, if I'm instructed to use the addition method, the least common multiple, or what will 2 and 5 both go into, is 10. I would have to multiply this one by 5, this one by 2, one of them negative. The least common multiple for y's is 12. Multiply this by 4, this by 3, one of them would need to be negative. In other words, you didn't have an example where both of them had to be changed, but in this example you would. Let's suppose that I decide that I want to target the x's. I would need to multiply the top equation by 5, the bottom equation by 2. That would turn them into 10s. One of those needs to be negative, and it doesn't matter which one. So I've just chosen the 2. 5 times 2x is 10x. 5 times 3y is 15y. And 5 times 5 is 25. Negative 2 times 5x is negative 10x. Negative 2 times 4y is negative 8y. And negative 2 times 8 is negative 16. Then I would add, those would go. I would have 7y is equal to 9. Divide by 7, and y is equal to 9/7. Now, this is just an example problem. really just to illustrate what it's like when you have to multiply both equations by something. You would go on, you would now find x, choose an equation, say 2x plus 3y is 5, plug in. I have 2x plus 3 times 9/7 is equal to 5. Okay, not real pleasant. Put the 3 over 1. So I have 2x plus 27/7 is equal to 5. If you did not want to deal with fractions, you could multiply every one of these terms by 7. That would give me 14x plus, the 7's cancel, 27 is equal to 35. Subtract 27 from both sides. I have 14x is equal to 8. Divide by 14. It doesn't go in, but you can reduce that to 4/7. The answer to this made-up system, I made this one up, you're not going to have this one, is 4/7, 9/7. Kind of a unpleasant process, but I wanted you to see you won't always get fractional values in these problems, but there were lots of things I wanted you to see in that slightly more difficult example.